Today, we're diving into Quicksort, an algorithm that's absolutely legendary in computer science for its incredible speed. But here's the kicker. It has a secret, a surprising and honestly potentially catastrophic flaw that makes its name, Quicksort, seem like a total paradox.
And that really is the central mystery, isn't it? How can something with such a well-known, terrible weakness be the go-to choice for speed? It's kind of like calling a sports car the Flash, even though you know it has this weird tendency to just completely grind to a halt on a perfectly good road. So let's unpack that.
Okay, so this table lays it all bare. The best and average cases, O of n log n. That is fantastic. That's the gold standard for comparison sorting. But then you look at that worst case, O of n squared. That is a huge red flag. I mean, that's the same performance as some of the most basic, notoriously slow sorting algorithms out there. So what is going on?
Well, Quicksort's elegance and its speed all come from this one simple but incredibly powerful strategy: divide and conquer. The idea is, instead of trying to sort one massive, messy list all at once, you just break it down into smaller, much easier problems.
The whole process really boils down to three simple steps that you just repeat over and over. First, you pick an element from your array. We'll call that the pivot. Second, you shuffle everything else around that pivot. And third, you just do the whole thing again on the smaller pieces you just made. That's it.
All right, let's make this real. Imagine this is our unsorted array. Step 1, we need a pivot. Now, there are a bunch of ways to choose one, but for now, let's just grab an element, say the number 6, and make it our pivot. Simple enough.
Okay, now for the most important step, partitioning. The goal here is to completely rearrange the array so that every single element that's smaller than our pivot ends up on its left, and every element that's bigger than the pivot ends up on its right.
And voila! After just one round of partitioning, look what happened. Our pivot, the number 6, is now in its final perfectly sorted position. Everything to the left is smaller, everything to the right is larger. Now, sure, those two little subarrays are still a mess, but we've made some major progress. And here's where the magic really happens. This is recursion. We now apply the exact same logic, pick a pivot, partition, to that smaller array on the left, and then do it again for the array on the right. We just keep breaking the problem down into smaller and smaller pieces until we're left with tiny arrays that are already sorted. At that point, the whole thing is done. Okay, that process seems pretty elegant, pretty foolproof, right? So how on earth can it go so horribly wrong? Well, it turns out if the divide part of divide and conquer fails, the entire system just collapses. It all comes down to the pivot. The entire efficiency of Quicksort hinges on that pivot splitting the array into two roughly equal halves. If you consistently pick a bad pivot, like, say, the smallest or the largest element in the array, then you're not really dividing the problem at all.
So just imagine this scenario. Someone gives you an array to sort that's already sorted, and your strategy for picking a pivot is to just always grab the last element. What happens? Well, all the other elements are smaller. So you end up with one giant partition with n-1 elements, and a completely empty partition on the other side. You've only shrunk the problem by one element. You have to do this over and over, and that's exactly what gets you to that dreaded O of n squared.
This slide visualizes it perfectly. On the left, that's what we want. A good pivot gives you a nice, balanced tree, splitting the work efficiently at every level. But on the right, that's the disaster scenario. A bad pivot gives you this totally lopsided, skewed tree. It's basically a linked list, and all the powerful benefits of divide and conquer are just gone.
So, you're probably wondering, if the basic algorithm is so vulnerable, why do we still use it everywhere and call it Quick? Well, it's because over the years, computer scientists have figured out some brilliant ways to tame this beast and make that worst-case scenario practically impossible to hit in the real world.
So instead of a naive choice like always pick the last element, modern versions are way smarter. You could pick a random element. That makes it super unlikely that someone could deliberately give you a worst-case array, or you could just pick the middle element. But a really popular and effective one is called the median of 3 method. The median of 3 method sounds fancy, but it's dead simple. You just look at the first, the middle, and the last elements of your current array, and you pick whichever of those 3 is in the middle to be your pivot. This tiny bit of extra work almost guarantees you won't pick the absolute worst element, and it immediately solves the problem of trying to sort an already sorted list. And if you want the ultimate safety net, many programming language libraries use a genius hybrid algorithm called IntroSort. It's basically Quicksort, running at full speed, but it keeps an eye on how many times it's recursing. If it notices that things are getting too lopsided, a sign that we might be heading towards that n-squared cliff, it just seamlessly switches over to a different algorithm, heapsort, which guarantees O(n) log n performance no matter what. It's truly the best of both worlds.
Okay, so with all these safeguards in place, how does our souped-up Quicksort stack up against its main rival, MergeSort? MergeSort is famous because it has a guaranteed O(n) log n performance right out of the box. This is where cool theory meets the messy reality of actual computer hardware. Quicksort's first huge win is memory. It's what we call an in-place sort. That means it just shuffles the elements around inside the original array and only needs a tiny bit of extra memory to keep track of the recursion. MergeSort, on the other hand, actually has to create a whole temporary copy of your data to do its work, which could be a huge deal for large data sets. The second, and often the deciding factor, is something called cache locality. See, that partitioning step in Quicksort scans through memory in a nice straight line. Modern CPUs are incredibly good at this. They can predict what you'll need next and load it into a super fast memory cache. MergeSort's memory access is a bit more all over the place, which leads to more cache misses. Basically, the CPU has to wait for data, and that slows everything down in practice. But MergeSort does have one very important advantage. It's what we call a stable sort. All this means is that if you have two equal items in your list, a stable sort guarantees they'll end up in the same relative order. Quicksort makes no such promises. It might swap them. For certain jobs, like sorting a spreadsheet first by one column and then another, that stability is absolutely critical. So here's the final takeaway. While MergeSort has that better theoretical guarantee on paper, for the everyday task of just sorting a bunch of stuff in your computer's memory, Quicksort's real-world advantages, its small memory footprint, and its cache-friendly nature often make it significantly faster. It wins in practice, and that's usually where it counts. And this really leaves us with a final, bigger thought. The story of Quicksort is a perfect example of a constant tension in all of software engineering. It's this beautiful reminder that sometimes the algorithm that looks the best on a whiteboard isn't actually the fastest on real hardware. It forces us to constantly ask, where do we draw the line between pure, elegant theory and messy, practical reality?